This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you so much for joining us for the Satellite Book Club Seminar Series. This is session number 162. The title of today's presentation is NESDIS Snowfall Rate Products for Nowcasting. We're glad to have Dr. Huan Meng, physical scientist from NESDIS STAR, with us today. Our facilitator of the discussion following the presentation will be Joe Moore, warning coordination meteorologist at the Forecast Office in Duluth, Minnesota. As you just heard, this session is being recorded, and there will be opportunity for Q&A after the presentation. If you have not signed in with your full name, please note that when asking a question in the chat so we can follow up as necessary. We're always looking for future presenters. Please contact our Tower S team, Krishad Bowman and Emily Maddox, if you would like to present as part of the book club. And if you're looking for training materials, Ross Van Til can help with that. I'd like to thank our Tower S team, Krishad Bowman and Emily Maddox, the Office of the Chief Learning Officer, GOZAR, JPSS programs, our presenter, facilitator, and all of you for being with us today and hopefully helping us with an engaging discussion following the presentation. I would like to note, with the impending government shutdown, the Satellite Book Club will be suspended for the duration of that time. Please keep an eye out for communication from the Tower S team regarding the temporary suspension of the weekly sessions and when the Satellite Book Club would resume. Of course, we certainly hope that there is not a shutdown, and of course, for all of my federal colleagues, we all hope we continue to be paid. All right, without further ado, let me introduce Dr. Huan Meng, is a physical scientist at the NESDIS Center for Satellite Applications and Research, or STAR. Her research area is in passive microwave remote sensing, and she's been working with a team of scientists at the Cooperative Institute for Satellite Earth System Studies, CISESS, at the University of Maryland to develop both satellite-based and radar-based merged snowfall rate products. Juan, we're glad to have you back at the Satellite Book Club.
Thank you, Jordan. Hi, everyone. I'm Huan Meng, and I work for NESDIS. And so today I'm going to talk about the snowfall rate products we have developed. And first, I would like to thank my colleagues and our collaborators, and there are many of them. So I gave this a similar talk about 3 years ago at Tower S, and I thank the Tower S team for giving me an opportunity to present the updated talk. And so we have two snowfall rate products. One is a satellite only. We call it SFR. The other one is a merged radar and satellite product called the mSFR. And both of them are liquid equivalent snowfall rate estimates, so they are QPEs. I'll start with the SFR product. It is derived from passive microwave measurements. So we have 10 polar orbiting satellites to derive this product. The advantage of the passive microwave is it can penetrate clouds. So it has it can actually sense the in-cloud precipitation. So that's unlike a visible. So from our analysis, we find that the best correlation between the SFR and the radar snowfall estimates, there is about 30 minutes time shift. So I'll talk more about that later. SFR resolution is sensor dependent. It ranges from 4 kilometer by 7 kilometer to 16 kilometer and later. snow now in Alaska. The last one shows the equator crossing time, ascending mode only for some satellites, and the red arrows points to the satellites we use for SFR. So you can see they're not evenly distributed in time. We have done a lot of developments since my talk about 3 years ago. So the SFR is derived actually from 2 algorithms. One is for snowfall detection, the other one for rate estimation. And for snowfall detection, we use machine learning. So overland target is the manual weather reports from NOAA's ISD dataset. Over ocean, we use the spaceborne radar, derived precipitation flag, and it's a known good product. And the input for the machine learning models are the satellite observations and some GFS model data. That mainly is like temperature, relative humidity profiles, and things like that. We don't use any model precipitation predictions. We tested several machine learning models, and based on the performance, we selected the XG boost. And then we run the validation study, and here are the results. The plot on the left is the Hikey skill score from the SNPP satellite over land. The different colors represent different machine learning models, and the red is the XG boost model. And as you can see, well, we group the data by 2-meter temperatures because the performance is temperature dependent. When it gets really cold, the performance degrades. And so the minus 15 degrees Celsius is about 5 degrees Fahrenheit. So that's pretty cold. And so when it's warmer condition, the Hikey score can get up to 0.8 or higher. And but even when it's cold, it can still be about 0.6. The figure to the right is the performance over ocean, and again, data are grouped by temperature. But the overwhelming majority of the data is when the 2-meter temperature is above minus 5 degrees Celsius. That's about 23 degrees Fahrenheit. And the different colors represent different surface type. And usually over open water, the performance is the best, better than over sea ice and coast. For the rate estimation algorithm, we started with a physical-based model to retrieve cloud properties from satellite data. And then based on that, we derived the initial snowfall rate. And then there is the last piece is a bias correction model. And for that, again, we use machine learning. And the input includes both satellite observations and GFS model data. These are the validation results in the scatter plots. On the left is from CONUS. We use CONUS as a target and as the validation data set. And it's CONUS. It's CONUS only because it's a stage 4 is the data we use. And so the correlation coefficient is 0.68. And well, actually for both, the figure to the right is over global, both land and ocean. So for both, the correlation coefficient is about 6.5 or higher, and with reasonable root mean square error and low bias. So we're happy with the performance. So with all these developments, we get to eliminate a temperature constraint. The previous algorithm was only applicable if the 2-meter temperature is greater than 7 degrees Fahrenheit. And we also are able to extend SFR to over water previously we only had the land coverage. So the most important part of the development is now we significantly improved the product accuracy, both in detection and read estimation. And we also are able to reduce the latency by using direct broadcast data. And we get the direct broadcast data from University of Wisconsin. And SPORT distributes the SFR data via LDM. SFR is also generated at GINA, University of Alaska, Fairbanks, and they use their locally received DB data to generate SFR and distribute it to the NWS Alaska offices. So the latency for CONUS right now is about 30 to 50 minutes and 30 minutes for Alaska. And this is from the time of the satellite measurement to when the data shows up in the AWEBs in the local in the WFOs. So we are also making effort to further reduce the latency. So here's these images show the different version of SFR. The first one is the previous version. The different shades of gray are all different areas where we couldn't do retrieval, either too cold or over water, so you don't have anything over, say, the Great Lakes. And then, so in the middle is the current most up-to-date SFR we have, and so it doesn't have all those constraints anymore. And if you look at, well, the one to the right is the NORSC hourly snowfall rate, and if you compare the two, you can see so that's one. If you compare the current SFR with the NORSC, there's lots of similarity between the precipitation pattern and the rate, much better than the previous version. And to ask that question that just popped up, the latency is from the time the satellite takes the measurement to when the product shows up in your local office AWEBs. So yeah, that's the whole delay there. Well, truth is basically the best data we can get our hands on. So for for overland, we use like I said, we use a stage 4, and stage 4. Where did I have that? Well, I'm sorry. For snowfall detection, we actually use ISD. So it's yes, no, and this is we only use manual weather reports because we found those automated report have larger errors. In over ocean, we use the NASA CloudSat. That's a spaceborne radar precipitation flag, and that's also a very good data set, at least in terms of detection. And for snowfall read, for the bias correction, I actually don't have it here. For the bias correction, we also use both stage 4, that's the hourly, and also the spaceborne radar derived precipitation rate. Those are what we used. But when we did the validation, we used the stage 4, and we used the ECMWF reanalysis, the ERA5. And these results are very reasonable. So yeah, I've got this one. Okay, so now going to the next, the second product is called mSFR. So we merge this radar and satellite. And the radar is the MRMS instantaneous precipitation product, and that was developed by the National Severe Storms Laboratory. We only use the snow data from there, and the satellite is the SFR. You probably all familiar with this. The MRMS is a QPE, and it's derived from about 180 radars, and it has high resolutions, 1 kilometer every 2 minutes. But it does have issue with coverage in the mountains, and also when there's snowfall, it tends to the quality tends to degrade. So to the right is this quality, the radar quality index during this East snowstorm. And you see how in the West, there's always poor coverage. In the East, when there's precipitation, well, when there's snowfall, the QPR also decreases. We developed the mSFR in response to forecasters' need for looping capabilities. We understand that's very important for forecasting. And we, by merging radar and satellite, we, take advantage of the best part of both products. SFR can fill in the radar, the MRMS gaps, and the MRMS can ensure the high temporal resolution. So the final product, the mSFR, is 10 minutes refresh rate. So there's that looping capability to track storm. So the images on the left is the mSFR, in the middle is the MRMS, and on the right is the NORSC hourly we use to compare. So there's some snow in this the area that's in the magenta oval there, but that's missing in MRMS. But when satellite comes through, then that snow is filled in. So when you compare with the NORSC, there is indeed a snowfall in that area. So we use a pretty simple merging technique right now for mSFR. We start with the MRMS grid, then we do the QC. Basically, we set flag if the QPR is less than 0.3 or there's no snowfall. There can be rain, but that does not, we don't take that as a snowfall, obviously, so we set a flag. So we put the QC, the MRMS on the grid, and then we add SFR wherever MRMS is flagged. Important thing to point out here is the SFR and MRMS have a time lag between 25 and 35 minutes. And this is because satellite is mostly sensitive to snow in the atmosphere. And so we did this analysis, like in this plot. The blue is the correlation coefficient, the red is root mean square error. And then you put everything together, then the 30 minutes seems to be the best choice. So we designed the mSFR with this time lag to make sure the two can match better in time. Temporal resolution is 10 minutes. Latency is 5 to 7 minutes on average. And again, this is the latency from the measurement to when the data shows up in the AWEBs at the WFOs. And this is a CONUS only product because of MRMS. This is AWEBs, mSFR AWEBs like a display. You see the satellite swath there and merge the radar and satellite. And the way to differentiate between SFR and MRMS is by the spatial resolution. SFR always has coarser resolution than MRMS. So these products can be used for nowcasting. They are observation-based and they have low latency, and the mSFR also has the looping capabilities. So they can provide situational awareness during snowstorms. And they're especially useful in areas when you don't have good ground-based observations. And this is because of the satellite contribution. And the SFR can be uniquely valuable for nowcasting or short-term forecasting because satellite is sensitive to in-cloud snow. So these products are generated in near real time right now and distributed via LDM. And TowerS, in collaboration with Sport, has implemented SFR and mSFR in their AWEBs, and they will include them in the TowerS RPM version 24. And I heard that's going to be in the November release. So these products are also posted online and with the low latency. There is the CISESS University of Maryland website, and I'll show that a little more later. And also Sport has two websites to show the SFR and the mSFR. This is what the TowerS menu structure looks like for the SFR and the mSFR. This is in their version 24 release. So you're probably familiar with how this works. And then this is you go to the satellite and then the polar derived products there, and you will see snowfall rate. And you have the snowfall rate here is the SFR, and then you have the mSFR down here, and with the liquid equivalent and the three SLRs. Okay. I think, did I miss one? Oh, okay, no. All right, so the product, we also had the product assessment a few rounds in the past at WFOs. And so most recently, we had one at the Juneau, Alaska WFO, and also the Alaska Pacific Real Forecast Center. This was last winter for 1 month. And so forecasters assessed SFR in their operational environment. So they submitted feedback. They only have access to SFR because mSFR is CONUS only. And so there were 8 evaluations. And so to the right, these images were submitted by one forecaster. And he compared the AKSFR is just the up-to-date SFR. The operational SFR is still the old, the previous version. So he compared the two, and so the current SFR did better with the snowfall identification and the rate. Apparently there was still some overestimation of snow identified. The temperature was actually quite warm. And this is probably an issue with the model temperature because that's what we use. But the updated SFR definitely performed better than the operational SFR. And this is forecasters' responses about one question to one question about SFR utility. And most of them think SFR is helpful, is useful, either very useful or useful. So this is the CISESS SFR and mSFR website. It is Google Maps based, so you can use all the functionalities comes with the software, and it displays SFR over CONUS and Alaska, and also mSFR over CONUS. The latency is the best on this website. You have less than 20 minutes and for SFR, and about 2 minutes for mSFR. And so it's not, currently it's not AWEBs, but it does have some nice features. You can loop, you can zoom, and you can even sample the values when you click on the point, and you can generate GIF image animations and display county boundaries. And you have to zoom in some and then start to show the county boundaries, etc. And the website also includes training materials and some documentation. It has an archive back to about October 2020 for SFR and January of 2022 for mSFR. Some satellites can go back even further, but these are for sure you will see images from these days forward. And we continue to develop the products. For the mSFR, we haven't been able to do much in the last 3 years also, but we are making a real effort on this front. We are enhancing the mSFR, the MRMS precipitation phase detection. There can be some misidentified precipitation phase there, so we are making some effort there. And we use GFS data and machine learning techniques for that task. And we're also trying to improve the techniques for merging SFR and mSFR. So you can see at the bottom here, there's this plot on the left that shows the MRMS Snowfall rate is a function of the beam height, the lowest beam height. So it does go down as the radar beam gets further away from the radar. So in the first, in the middle here, it shows if we use all MRMS merge with the SFR, and at the end of that, the values, the snowfall rates start to go down towards the edge, and then when it meets with the satellite, then there's the jump. So to the right is when we limit that beam height to half kilometer, about 1,600 feet, then the satellite and radar can meet together much nicer. So this is ongoing research. We're still trying to figure out what's the best way. This is just one aspect of it. For SFR, besides working on the algorithm, we are also we work on new missions when there are new satellite launches. And here's just a laundry list of the satellites we can use in the next few years and beyond. One thing I want to mention is the small sat constellations. That's becoming more and more the direction people are going. Instead of those very large $1 billion, $500 million missions, now they launch a small sat, and there are lots of things to work through, validation, calibration, things like that. But that's the direction, and we're excited about it, because the more for precipitation, the more satellites, the better. And this is just something I want to throw in there. It shows in the next few years we're going to have new satellites come up, and how they can fill in those temporal gaps, and we can, not too long a distance in the future, we hopefully can reach 1 to 2 hour refresh rate, and that would be great. So in summary, we have a SFR product from 10 satellites, and that can provide about 20 snowfall rate estimates in mid latitudes and more in high latitudes. And SFR is merged with the MRMS to produce a spatial temporally enhanced mSFR product. These products can assist nowcasting by providing situational awareness during snowstorm and filling ground observation gaps. And SFR also has the potential for short-term forecasting. And then we continually develop the algorithm and enhance the product, and also add new satellites. And also TowerS will include the SFR and mSFR in the RPM version 24 in November. And there's this acknowledgement to our founders, and thank you.
Excellent, Juan. Thank you so much. So I want to encourage attendees to stay on. We do have, we'll get to some questions here in a moment. If you do put a chat in with a question, just be sure to add in your office name and your name, usually your name's associated with it. But yeah, put your questions there in the chat. So before we get started with the questions, there is a survey that Emily is going to post in the chat room with some feedback for the Satellite Book Club. It's a very short survey. If you have a minute to share some feedback before we get done here, we really appreciate it. Again, a week from today, on Thursday, Peter Rogers, the WCM, my colleague from the Sioux Falls office, is going to be discussing the Power on the Prairie Air Show, and their decision support for that, prediction, communication, and decisions. So I'm looking forward to that one. I also want to encourage you, if you've any questions, to please contact the Tower S team, Kashaw Bowman and Emily Maddox. If you have any questions about the Satellite Book Club, if you'd like to do a talk on the Satellite Book Club, and any questions with configurations for satellite products. So let's get started with a couple of the questions. And I think there was an early one. David Donahue was asking, why do you suppose the performance is best over the open ocean? Because it has something to do with the surface emissivity is more homogeneous than other surface types?
Yeah, that's definitely one reason. Probably most important reason. So over sea ice, especially over coastal area is so complicated, and the satellite gets all this mixed factors in there, so it becomes hard to just to extract the snowfall information. And ice is also a very complicated surface, because you have the different multi-year ice, thin ice, and new ice. So yeah, just because the signals are too complicated.
Right. Doug Kahn asked, will the merged snowfall rate product be able to incorporate Canadian radars, given that they were part of MRMS? I think they're temporarily not in the MRMS composite, but I would assume so. I don't know if you had anything to add to that. I see it in the archived imagery that the Canadian radars are part of the merged satellite or snowfall rate product.
Yes, yeah. Whenever we whatever we get from MRMS, we use it, and as long as the Canadian radars are included in MRMS, we're using it.
Excellent. Scott Lindstrom asked, that is it correct to assume that the parallax shift from the microwave detection of the snow is small because the detection is fairly far down in the cloud, and what it's actually detecting is closer to the surface? So the parallax, so that it's a small parallax shift that we're seeing. Yes,
we don't usually consider that, and also because the satellite footprint is large, with passive microwave, so parallax is probably it's a fraction of that. So we don't really. Awesome. Yeah.
Jorel asked, do you know when or if the NOAA 21 data will be added to the snowfall rate product?
Okay, so we're working on to add it, but the provisional, Jorel, in the NOAA, the provisional review, provisional maturity is when if we pass that, then the product is supposed to be operational. So ours is that review is scheduled for February next year. We're trying to move it a little earlier. So at least because we're evaluating the results. If we're happy, we're going to add it to our processing system, which is now considered the NOAA, the NESDIS operational stream. So we're, by the end of the year, that's our target. We're going to add it to the SFR and propagates into mSFR.
Excellent. Do you have to rederive the machine learning algorithms with a different satellite, or because the sensors are similar to NOAA 20, I'm guessing? Is it fairly plug and play?
Yeah, well, I mean, we ideally, actually, for every satellite, we actually develop its own algorithm, use its own data. NOAA 21, we have some data. We'll have to see if we have enough to develop its own. And if not, we may add some NOAA 20 data in there, but it's still going to be NOAA 20's own algorithm.
Excellent. John Forsyth asked, will the higher frequencies between 200 to 600 gigahertz, like on the upcoming MEDOPS SG series, improve the retrieval?
Yes. We haven't been able to do any, we haven't got supported to do that analysis, but from the analysis I see people did for rain, you know, that's supposed to be a very good channel. You know, those will definitely help.
Awesome. Oh, and Eric Goyette was just asking what's the current refresh rate? I think you said it kind of varies depending on the passes, right?
Yeah. So you have, you know, like between NOAA 20 and SNPP, you have like right now, I think it's 25 minutes, you know, some can be like that, or it can be, you know, as large as, you know, about four hours. So, you know, it very much depends on, you know, what time of the day, you know, when satellite comes by.
Excellent. If you could just go to your contact information slide, if forecasters have some feedbacks or questions on this product, who would be a good person to contact?
Sorry.
Yeah, you're good.
So I have to go all the way, scroll all the way to the front. Okay, so at the bottom there, you see my, is your display changing? Okay, yeah, so at the very bottom there, on the left, that's my email, just my name, HUAN.MENG.
We're not seeing it. You may have to reshare your screen.
You don't see it, okay. You know what, you can also go to, sorry, I have to go through it. You can also go to our website right here. Do you see this? The sfr.umd.edu.
Yeah.
And if you go to that website, there is, I think it's under About. You will see our team, and you can go in there. You know, every team member's email should be there, and you can send us feedback. And another thing I should mention is we're going to add a tab here on this website as you know, for feedback. And it's going to be a Google form, so you can go there, and if you look at the product, and you have some feedback, or if you use them in your operation, we would really like to hear what you think about the products. And you can also, yeah, add attachment, you know, things like that.
Awesome. Yeah, no, I'm very much looking forward to having this in AWIPS. So we have radar gap issues here in Minnesota and Wisconsin, so it's going to be really useful this winter to easier evaluate it in real time with it being in AWIPS. So
great.
I'm going to turn it back to Jordan for some final remarks. So thank you, Juan.
Mm-hmm.
All right. Thank you so much, Juan. Thank you so much, Joe, for facilitating that discussion. I was glad to see so many questions and so much interest in this product. So thank you to everyone for attending today. As has been mentioned, if there is no lapse in appropriations, we will continue with the Satellite Book Club next week, normal time, Thursday, October 5th. We're going to be talking about Prairie IDSS. So please tune in next week if we are open. And if, in the meantime, if you have any questions related to the configuration of satellite products, the TowerS team is able to help. Some of our TowerS team members will be also available during a potential shutdown as well. If it is mission critical, Kashad Bowman, Emily Maddox can help with that. So please feel free to get in touch with them if you have any questions about this or any other satellite products. With that, we'll wrap it up for today. Happy